So, input impedance and admittance. This chapter is impedance-based modeling. And the idea with this chapter, chapter 5, is that we want to get to a transfer function. Okay, this is the main idea. We want to get to a transfer function without having to go through the whole state space model and all that, and then transforming that into a transfer function. So we want to be able to go straight to a transfer function and sort of take a shortcut there, and that's what this allows us to do. It's very much analogous to impedance-based modeling of circuits. So like, if you guys remember that whole business, sometimes people call it AC circuit analysis. That's essentially what we're doing now, but for like all systems, okay? So it may be familiar, hopefully it is. Some of the terminology is the same, and you can think of this as being a generalized version of so-called AC circuit analysis. So, let me just make sure, yep, okay, got my voice. Hear me? So we now introduce a generalization of the familiar impedance and admittance of electrical circuit analysis, in which system behavior can be expressed algebraically instead of differentially. We begin with generalized input impedance, which is kind of the foundation. So consider a system with a source as shown in figure 5.1. Let's take a moment, look at this figure. So there's some system which I've represented by this sort of rectangular oval. And there's a source connected to it. I didn't say if it was a cross variable source or a through variable source. Could be a voltage source, could be a force that's being applied to the system from outside. And we always have associated with one of our sources a cross variable and a through variable, regardless of whether or not this is, or of whether this is an cross variable source or a through variable source. Both are there. So even when you have a voltage source, which is clearly an across variable source, we still have current being supplied by that voltage source. So similarly, whenever you have a force source, there's still a velocity associated with it. So this is our situation. We have, I'm using these generalized variables. So f is a generalized through variable, and I'll draw it with a script f like that. And then v is a generalized across variable. So if this is our source for the system, we can look at this in more detail. So the source can either be across or through. The ideal source specifies either f in or v in, and the other variable just depends on the system, right? So if it's like 5-volt source, then you're always going to assume, if it's an ideal source, you always assume that there's 5 volts being supplied and that the current depends on what you connect it to. So remember, if you just short it out, if you just had a 5-volt source and you just connected a wire in between the two terminals, then it would be essentially impossible for that source to maintain a 5-volt difference. It would be flowing infinite current to make that happen. So that's why it's an ideal source. But typically we don't short it out, so it's better approximation. Okay. So let a source have across and through variables v in and f in. So notice I'm using of s here. So I'm already looking at the Laplace variable, the Laplace domain aspect. So you can always take the Laplace transform of any function, right? So we take the Laplace transform of each of these. We define the system's input impedance z and input admittance y to be the Laplace domain ratios. The impedance is the across variable over the through variable, and the admittance is the through variable over the across variable. Clearly, y of s, the admittance, is the reciprocal of the impedance, right? both z and y can be considered transfer functions. For a through variable source, Fn, the impedance z is the transfer function to a cross variable Vin. Okay? Remember, output over input is our definition of a transfer function in the Laplace domain. So it's in the Laplace domain. We have a transfer function already there. For an across variable source Vn, the admittance y is the transfer function to through variable Fn. Often, however, we use the more common impedance z to characterize systems with either type of source. So we don't necessarily use impedance, or we don't necessarily use admittance at all. We often just use impedance. I think that impedance is a little bit more intuitive for us. And primarily the reason for that is that resistance is impedance. So it's a type of impedance. And it's common for us to be intuitive about resistors versus thinking about how well something conducts. Thinking about how well it resists is a little easier for us. For whatever reason, probably just because that's what we're used to. Okay, so note that z and y are system properties, not properties of the source. An impedance or admittance can characterize a system of interconnected elements or a system of a single element, as the next section explores. So we're going to say, okay, this system, we're just going to put a single element in there. And we're going to see what happens, what type of input impedance is. And we're going to put elements that we're familiar with. Okay? So, the impedance and admittance of a single ideal one-port element, and not just an element, an element. That, just a typo. Is defined from the Laplace transform of its elemental equation. So that is a very important fact, okay? So the impedance or admittance is defined from the Laplace transform of this elemental equation. So you take the elemental equation, take the Laplace transform of it, you find the ratio of the across variable to the through variable, and you've got yourself an impedance, the input impedance for that element. So we're going to talk in terms of generalized elements. So we've got generalized capacitors, generalized inductors, generalized resistors. Generalized resistors. And remember that we've drawn this parallel in the past where we've said, capacitors are like masses, and masses are like fluid capacitors, and fluid capacitors are like thermal capacitors. They're all kind of the same thing. They all have this elemental equation where the across variable is time differentiated, and it's equal to some ratio of the capacitance multiplying the through variable. So this is our generalized capacitance equation, elemental equation. They all look like this. So this could be, if it's a voltage, it would be, for an electronic capacitor, it would be dVc dt equals 1 over CIC. If this was a mass element, then it would be dVm dt, which is say the acceleration is equal to 1 over the mass times the force on the mass, etc. Right? So this is describing all of those in one equation, this generalized capacitor equation. So we've got this expression, and we're going to take the Laplace transform, right? That's what I said we do. We take the elemental equation, Laplace transform. Pretty easy when you've got a simple equation, right? Left-hand side, there's a time derivative. So you have an s that pops up. Just one time derivative, so just one s. S Vc of s now. So this is now the Laplace transform of Vc. We're already using capital scripts, so we don't have nowhere to go. So we just got to do of s. It's our only notational option there that's any good. And then on the right-hand side, we have a constant. So that's, remember, Laplace transform is an integral, so we can pull the constant out front. 1 over c. Laplace transform of FC of t is just FC of s, just by definition. That's how we denote the Laplace transform of FC. And we can solve then for the impedance, which is VC over FC, and the admittance, which is FC over VC. Of course, they're reciprocals, as before. And we get that. What do you guys have? VC of S is equal to what? 1 over CS. Very good. And YC of S is equal to what? CS. Very good. So, like I said before, we mostly focus on the impedance, but knowing what the admittance is doesn't hurt anything. So. Okay. Generalized inductors. A generalized inductor has this elemental equation. So once again, if this was an electronic inductor, it would be DIL dt equals 1 over L VL, right? If we had a fluid inductor, which is called an inertance, right? This is the thing I screwed up in the video. I often just call it an inductor because it's a generalized inductor. But if we had that situation, it would be dqi dt equals 1 over I times pi, right? Okay, so these are just a couple different examples of these generalized inductances, so generalized inductors. So we've got a time domain equation, 5-4. The Laplace transform, just simple again. There's a time derivative on the left-hand side. There's S times FL equals 1 over L VL. And we can solve that for the impedance ZL, being the ratio of VL over FL, and then similarly the admittance. So ZL is what? LS, good. And YL, 1 over LS. Great. There's a nice symmetry here, right? Between the generalized capacitor, generalized inductor, they're kind of like flipped. Okay. And now we have the generalized resistor. So the generalized resistor, for an electrical system, it's just a regular old resistor. For a mechanical system, it's 1 over the damping ratio, or the damping coefficient, I should say. So the resistance R is either in ohms or in 1 over whatever the units of BR, I can't remember off the top of my head. They don't have damping ratio, does it? Damping coefficient does. Yeah. It's force per velocity, yeah. So, okay. Generalized resistor has this. So it's the cross variable is proportional to the through variable with constant proportionality R. Laplace transform of that. Oh, look, there's no derivative, so no S's come in, so it's just kind of the same. So the impedance ZR and admittance YR are what you would expect. So ZR of S is equal to what? R. And the admittance 1 over I. So that is, we remember that from back when we did so-called AC circuit analysis and we looked at impedances of electronic elements, and the impedance was a resistance, right, for a resistor element. Okay, now we're going to connect them up. So we've got, for a minute there, we were just pretending like the impedance and admittance, we were just talking about one element as our whole system, but now we're going to expand that. So say we've got more elements interconnected here. by the way, the term interconnected, I'm uncomfortable with. Because how is that different from connected? And I looked up on the internet, and there are people who violently defend the use of interconnected when you have a network of more than just two things being connected.
Sounds like you're describing a political debate.
Yeah. I mean, we could go there too. I pretty much have given up on the human race. So, sorry, that was overly negative. Just humans that are alive now. That's better. Okay, so I'm not as pessimistic as I sound. I laugh so I don't cry. Okay, so impedance of interconnected elements. As with electrical circuits, impedances of linear graphs of interconnected elements can be combined in two primary ways. The familiar parallel and series, right? You know, you guys are getting bored now, right? It's like same old stuff, same stuff. Yeah. Elements sharing the same through variable are said to be in series connection. And elements connected in series, like this, have equivalent impedance Z and admittance Y. So you sum up the impedances in series, and you take this 1 over the sum of the reciprocals of the admittances in series. Okay? Conversely, elements sharing the same across variable are said to be in parallel connection, and elements connected in parallel like this have equivalent impedance and admittance, as in 5-9, which is to say the familiar 1 over the sum of the reciprocals for the impedance and just summing up the admittances. Okay. Let's do an example. So for the circuit shown, find the input impedance. Okay, so we've got ourselves 4 different elements. We've got resistance, capacitance, inductance, multiple resistances, some stuff connected in parallel, some stuff connected in series. Okay, so what do we do?
Start by combining the two in parallel into a single input form.
Yes. So there are different ways to go. I mean, you could do this thing step by step, which is probably the right way to go, which is you combine these together and then you combine them. So combine these in parallel and combine these in series. Or we could do the way we shouldn't go, which we will do, and just do a one-liner. Yeah?
Yes.
Yeah, let's do one-liner. So, actually, my recommended way of doing this is not worrying about what the impedances are on the first go. Just go one-liner, but just not plugging in what the impedances are of each thing. So just say Z, R1, ZC, ZL, etc. And then we'll plug in what they are in the next step. Okay? So one-liner, we want the impedance is going to be the impedance from there to there, right? The impedance of the whole thing. So we got to go combine these 3 things together. So it's going to be the impedance of R1, so I would just say Z equals ZR1. And then they're in series, so ZC, right? Plus ZC. Plus, this is also in series with them, but they're in parallel together. So we got to combine them in parallel and then add them in series. So we could do the 1 over, but or we could skip a step and simplify it to ZL ZR2 divided by ZL plus ZR2. And like we're pretty much done, right? I mean, like that was the hard part. I don't know, no part's hard when you break it down, is it? They're all one-liners are fun. Okay, so then we could just say where. Whoa. There's also a W and an H in where. I just started right in the middle. It's okay. That's why we have undo. Not in real life, just in computers. Oh man, my friend brought a VR headset for I guess it was PlayStation VR. We played some crazy like shooting clown game, and like on these roller coasters, and we were shooting these crazy clowns and shooting balloons too. And oh man, I was really good. I mean, I felt like I was really good, which probably doesn't mean much because I think that that's the idea. But yeah, VR is crazy. Anyways, speaking of virtual, so we've got ZR1. What is ZR1? R1. What is ZR2? What is ZC? And what is ZL? Yeah. So it's plug and chug from there, right? Probably we should do all that, but you know, honestly, I'm not that worried about that part because you guys learned algebra before you got to this class.
We did?
Yeah. Aaron didn't. Others did. Aaron's just catching up now. I made a calculus joke earlier in an email. It was, somebody was like, there's this new policy that I've been pushing and almost have through in our School of Engineering, which is that in order for a class to count as a prereq for the next class, you have to have a C- or better in the class.
What is everywhere else?
Yeah, I know, right? So I was like, it's a pretty no-brainer policy, I think, but I was like, let's do this policy. And then there was somebody was like, well, but the school says that you have to graduate with a 2.0 GPA, so like you could get a 1.7 if you just have. I'm like, well, that's a minimum, and clearly, if you're gonna get a 2.0, you have to have some grades that are greater than C-, and I can prove it to you with the mean value theorem of calculus. So it was a good old calculus joke. We laughed. I laughed. It was an email, so we don't know if they laughed. Oh, professor email jokes. They're the best. So we are, I mean, this example, I don't know. What is this? I mean, if you work this out, it's going to be if you simplified it, it's going to be some fraction that's got some polynomial in S, right? And actually, can we predict? Well, we won't. Well, we could. It's second order system, right? We have an independent capacitor and an inductor. So it's probably going to be a second order system. So probably this transfer function, which remember that Z is a transfer function. The transfer function from the input Vs to the current that the supply is to Is, right? To the current that the source is supplying. So it's a transfer function in a second order system. The denominator is going to be second order. It's going to be a second order polynomial. So although we haven't been explicitly solving for transfer functions, like we haven't been talking much about it, we mentioned it, we are starting to see, I mean, this is like, this was really, really easy, right? And we got a transfer function like that just popped out of it. So if all you're looking for is a transfer function in a system, these methods are super powerful. Right? So far, we've only learned how to find a transfer function from the source variable to its other variable. So we have the sources, whatever its explicit type is. So this is a cross variable. If it's in a cross variable source, you can get the transfer function from Vs to Is. We don't have a general case of finding a transfer function yet, but we're going to learn that on Friday how to find any transfer function in the system. And it's very straightforward. So this is just one method that's very powerful to find a system model without going through all of the steps that we've done before. Yeah.
Sorry, I would look down when you wrote below that. Okay, U, is that US?
Oh yeah, so these are, I didn't mean to make these look like U's. They're just blank spaces.
Oh, okay.
So yeah, so I'm just saying that if you simplified this down, you're going to get some polynomial in S in the numerator and some polynomial in S in the denominator. Which is to say it'll look just like a transfer function. And that's because it is one. So, yeah.
So when you combine the impedances of the system, it just gives you the transfer function.
So it gives you the transfer function from Vs to Is. So between the two source variables.
Okay.
If you just combine them all up, if you look at the input impedance and you think of that as being the transfer function of the system from whatever the source explicit variable is to whatever the implicit one is, then it's the transfer function for you. But we want, for instance, often we care about what the transfer function is from Vs to like VR2. So far we haven't learned how to find that. We will learn, and it's going to be very similar to this process. But we can't just combine all the impedances. Combining all the impedances, oh yes, round 2. This is Ashley.
Alright. She's an enabler.
Yeah, I got 32 ounces of coffee this morning, and I only paid for 16. So today was a good day. You guys might have noticed that I'm a little bit more something today.
You have a crazy hour when you do that, that's good.
Yeah. Okay, so I think that's all we've got for this lecture. Let's move on to the next one.